signal set systems. So then in 1822, after 15 years of this submission date, his work, Fourier work, was finally published. And after that, up to 143 years, there was no significant work in the area of signal processing. In 1965, Cooley and Tukey, they developed fast Fourier transform, because people invented machines and computers now how to use this Fourier transform using machines, how to implement this Fourier transform with the help of computers and machines. So that was actually motivation for developing algorithms to compute the Fourier transform. And 1965, this Cooley and Tukey, they come up with the fast Fourier transform that is well known as FFT algorithm for computing Fourier transform. So this Fourier transform, we can represent actually this complicated signal in terms of simple signals. So this is here like basis functions are sinusoidal functions, and these simple functions, the main advantage when you have your signal is unknown, you want to use Fourier transform. For example, is T signal, and this is unknown signal, you don't know anything about the signal. But when you represent this signal in terms of sinusoidal functions, in terms of complex exponential functions, that these set of signals are known to you. So indirectly, what we are doing when we apply this transformation, we are converting this unknown problem to known problems. So that is the analysis becomes very simple. So this is actually this Fourier transform also can be considered as a bridge between time domain and frequency domain. And when you go from time domain to frequency domain, that process is known as analysis process. And when you come back from frequency domain to time domain, that process is known as synthesis process. So this you can see this mathematical expressions. So left hand side, that is the analysis. So we integrate actually this function signal which is defined in time domain, and we multiply with the complex conjugate of this exponential function and integrate with respect to time. So here we have integrated the signal with respect to time from minus infinite to plus infinite. So due to this entire integration for full range, there is no time in the frequency domain, because time is integrated. So there is no time in the frequency domain. Similarly, when you go for synthesis formula right hand side, we have integrated frequency from minus infinite to plus infinite. So there is no frequency in the time domain. So time domain and frequency domain both are disjoint. When you are in time domain, in Fourier transform, there is no frequency domain information, and when you are in frequency domain, there is no time domain information. So both domains are mutually exclusive. So this is one example. Here you can see that left hand side we have three sinusoidal functions. First one has a frequency of 5 Hertz, then second one has frequency of 25 Hertz, and third one has 50 Hertz frequency. So when we say frequency 5 Hertz, this means this is the sinusoidal of frequency of 5 Hertz. So you can see when you compute Fourier transform, the first case it shows the peak at 5 Hertz, and second case it shows the peak at 25 Hertz, and third case it shows peak at 50 Hertz. So this Fourier transform measures the similarity between your given signal and the designed basis functions. So what we do, we design various basis functions of different frequency values, and then we measure the similarity. So if any basis function is present in the signal, then corresponding coefficients will be higher. So that strength of the coefficient tells us the major, like whether it is major component of the signal or minor component of the signal. For example, strength of the coefficient, magnitude of the coefficient is 0. So this means this frequency component is not present in the signal. So indirectly it is measuring the similarity between two functions. One is known set of functions, and other one is unknown. So known is actually in our hand. So we design various functions and we measure the similarity. If any of these functions is present in the signal, unknown signal, then corresponding coefficient becomes higher. So that is actually that gives you spectrum analysis. So from that we can find out what are the different frequency components are present in the signal, and what are the different strengths of these frequency components. So that we have seen when you are in time domain, there is no frequency domain. When you are in frequency domain, there is a peak at different frequency points, but there is no time information. So actually in real life, signals can be classified in terms of stationary signals and non-stationary signals. And in signal processing, we use mathematical models to represent a signal. If the parameters of these models are constant with respect to time, then this signal comes in the stationary signals class. So any of the parameter of this model is changing with time, then it becomes non-stationary signal. So that is, for example, like sinusoidal functions a cos omega t, and it has two parameters, a and omega. A is known as amplitude and omega is known as frequency. So this a and omega, if they're constant, then it gives you stationary signal. If any of like a becomes function of time, then it gives you amplitude modulated sinusoid. If omega becomes function of time, then it gives you frequency modulated sinusoids. If both becomes function of time, a becomes a of t and omega becomes omega t, then it gives you amplitude and frequency modulated sinusoids. So that actually is modulated components have this time varying nature of the parameters, and this which has non-stationary nature of the data. So that is actually when you define the signals in terms of stationarity and non-stationarity, then this Fourier transform is misleading, because Fourier transform doesn't contain information about the time and frequency domain. So if your signal is changing with respect to time, due to that we have seen analysis integration is taking place from minus infinite to plus infinite. So entire time is integrated, so there is no time information in the frequency domain. So whether your signal is changing with respect to time or not changing, Fourier transform will be same. So that you will see with the help of an example. So this is an example where you can see left hand side two signals have been shown. One is stationary, second one is non-stationary signal. So in stationary signal, that same frequency components we have taken. It has 5 Hz, 25 Hz and 50 Hz sinusoid. This superposition of these three frequency components. And for a given this scale, all these frequencies are constant. They are not changing with time. So that you can see this frequency domain, it shows three peaks at 5 Hz, 25 Hz and 50 Hz. In second example, that is actually concatenation of these three frequency components. So first, like from 0 to 0.3 second, you have frequency 5 Hz, and 0.3 to 0.6 we have frequency that is 25 Hz, and then 0.6 to 1 we have another frequency that is 50 Hz. So this frequency is changing with time. In one segment it is 5 Hz, other segment it is 25 Hz, and third segment it is 50 Hz. So here it is a non-stationary signal. But when you apply this Fourier transform for stationary and non-stationary signal both, then you have same spectrum. So this spectrum doesn't tell whether this spectrum is corresponding to stationary signal or this spectrum is corresponding to non-stationary signal. So that is actually misleading, and this is the motivation for time frequency analysis. So this is also known as joint time frequency analysis, time dependent spectral analysis. And in French books they say this time and frequency domain actually they are married together. And they will stay together. They will joint stay, and both domains will stay together, and that gives the concept of time frequency representation. That is so. This is one way, and other one actually these sinusoidal functions they extend from minus infinite to plus infinite. They are periodic functions. So this time span what they cover, that is infinite. So this resolution is proportional to 1 upon area. So if you can see this time domain signal, in time domain the sinusoidal functions, which are the basis functions of Fourier transform, they adjust from minus infinite to plus infinite. Due to that, it covers infinite area in time domain. So due to that, resolution in time domain becomes 0. But on the other hand, in frequency domain, it has an impulse kind of nature. An impulse has like a 0 width in frequency domain, 0 bandwidth. So due to that, resolution becomes infinite in frequency domain. So these sinusoidal functions, they have very poor resolution in time domain, and they have very good resolution in frequency domain. And we want to have both resolutions together. That like we want to have time resolution also, frequency resolution also. So that is also actually one of the motivation for time frequency representation. So we will see this this first technique, the simple like first technique which was developed for time frequency analysis was short time Fourier transform. That is also known as STFT. And what in this technique we do, we have entire signal, and what we do, we divide signal into different segments, windows, and where we assume that the signal within the window is stationary. And stationary means its parameters are constant within that window, within that segment. And then we shift window to other locations, they take another segment, and we assume stationary, we apply Fourier transform. So in that way we cover signal with the different segments, and they can be overlapped also, so that you will have a smooth smooth STFT. There will be no discontinuity. So in order to have a smoothness in the time frequency representation, sometimes we allow overlapping also. Otherwise, it will be discontinuous time frequency representation. So here then this Fourier transform, we compute Fourier transform different parts or different segments, different windowed version of the signal. Then arrangement of these Fourier transforms of different parts of the signal gives us time frequency representation of entire signal. That is short time Fourier transform of entire signal. So here this is the mathematical expression of the short time Fourier transform. You can see xt is the signal that we want to analyze, and w is the actually wt is the window function, and t dash is the shifting parameter. So by t dash we are shifting this signal from one location to other location. So different values of t dash gives you different locations in the time domain of the signal. And where your window has finite, actually localized window in time domain, so you will it will not have infinite. So here this basis functions, like they have infinite span, they become finite span. So due to this use of window, so now these basis functions are windowed sinusoid. So the initial infinite spread, now they have finite spread, and that actually, so due to that time frequency domain, you can see that it becomes two-dimensional. One is frequency, that is like Fourier transform, and another one is t dash, that is time frequency. So this STFT, short time Fourier transform, it converts signal from one dimension to two dimension. One dimension here, that is time domain signal, and into time frequency domain. So now your signal is a function of time and frequency together. So that is actually, it is like a matrix or image kind of structure. This is one example you can see here. So this is the signal we want to analyze, and in the beginning it has high frequency component, and then middle it has low frequency component, and again it has high frequency component. So this window at you can see that t dash equal to -8 in the beginning, and we shift that t dash equal to -2 at different location, and t dash equal to 4, it is another location, t dash equal to 8. So in that, by using these 4 windows, we have covered entire time range of the signal, and we apply this Fourier transform to each window, and then arrangement will give you a short time Fourier transform. So this actually STFT is a complex quantity, and for representation purpose we take square magnitude of the STFT, that is known as spectrogram, and spectrogram is a nonlinear operator due to squaring operation, and STFT is a linear operator. And when you use this Gaussian window in STFT or short time Fourier transform, then this is known as Wavelet transform. And so this actually Gaussian window is the optimum window. Till today there is no other window which has same behavior in both domains. So like Gaussian window, which is the optimum window, because Gaussian window, if you apply Fourier transform, it is also Gaussian in frequency domain. So whatever transform you apply, it doesn't lose its structure. So due to that, it is also known as optimum window. And when you use any window, general window, then it is STFT. But when you use window by Gaussian window, then it is known as Wavelet transform. So that Wavelet proposed in 1946. This is one example of speech signal when you compute a spectrogram. So this is actually when you speak MATLAB, and this is the speech signal when you speak MATLAB. And luckily, these results are also obtained using MATLAB. So you can see this is the 2 spectrograms are there. First one is this left side is the time domain signal when you speak MATLAB, and right hand side upper one is narrowband spectrogram, and lower one or bottom one is the wideband spectrogram. So this upper one we are using large window in time domain. So due to that result, it will have narrow window in frequency domain, and due to narrow window and because it will have less area, and so the concentration, resolution, and focus will be more. So this frequency resolution will be high in the upper one compared to lower one. So that you can see also this whatever like speech signal, it has formant frequencies. and these formats can be identified nicely. In the bottom case, they are merging to each other. So that is a wideband spectrogram. So because due to wideband, resolution is poor. Resolution is proportional to 1 upon area. Band is wide, so resolution will be less. And this in time domain, you have short time window. So in that case, second case, resolution will be good in a time domain. And this is actually, these algorithm nicely can be implemented in MATLAB. In MATLAB, we have a spectrogram command. So you can try these results using this MATLAB code. And there's another signal that we can see, linear chirp signal. This signal is frequency changing with time in linear fashion. So you can see this this left-hand side signal in time domain, and it is not clear how frequency is changing. But when you take its spectrogram, and you can see this spectrogram using large window and this spectrogram using short window, and that you can see this narrow band large window results narrow band spectrogram, and the short window results wide band spectrogram. So in first case, when you use narrow band spectrogram, it has very good resolution compared to the bottom one. So that is actually the spectro. This there are two things. One is size of the window is required, and second one is the type of the window. That is also important in this. So this chirp command is available in the MATLAB. You can generate this kind of signal, and you can try spectrogram algorithm also. So which will give you nice time frequency plot for a given signal. Now, what is the problems with this short time Fourier transform? Actually, this short time Fourier transform, we have seen this, we obtain time frequency representation by computing different Fourier transforms at different segments of the signal. Now, what is the size of the segment? What is the size of the window? There is no thumb rule which will suggest us what should be the size of the window, what should be the type of the window. There are various options for windows, and we don't know which window should be used. And what is the size of the window, that also actually depends on the signal that we want to analyze. So due to these problems, there is no thumb rule, and it requires a lot of experience to do data analysis, to do signal analysis. So there are various actually we have seen also this wide analysis window. When you have window wide in time domain, it gives you poor time resolution, but it gives you good frequency resolution. Similarly, when you have narrow time domain window, that window short span, it gives you good time resolution due to less area, and it gives you poor frequency resolution. So now this is this window that we want to use for analysis, that is actually has fixed resolution nature. Once a window is selected for short time Fourier transform, you don't have option to change it. It is fixed for entire analysis. So that is now there are various windows in MATLAB. There is window function which can be used to see the various options like Wavelet window, Blackman window, Baumann window, Chebyshev, Henning window, Kaiser window, rectangular window, triangular window, Gaussian window, and we don't know which window is suitable for particular kind of signal. So that is actually, and also this spread in time domain and frequency domain of this window functions are associated by the Heisenberg uncertainty principle. So it says that we cannot have both time and frequency resolutions together very high. So if time resolution is higher, then due to that actually this principle, frequency domain resolution will become poor. On the other hand, if frequency domain resolution is very high, then automatically time domain resolution will becomes low. So this is actually this resolution. This is not in our hand. This is the limitation of the actually imposed by the nature in the form of Heisenberg uncertainty principle. So due to that, actually there is a problem in STFT. This resolution once window is fixed, and then your resolution is also fixed for all possible frequency components in the signal. So now how to solve this resolution problem? And then there was actually wavelet was proposed, and wavelet, this basis function or wavelet transform, which actually can be considered, wavelet can be considered adaptive window. So in wavelet we use scale parameter. So at low scale it gives you good time resolution. At large scale it gives you good frequency resolution or poor time resolution. So this actually is wavelet. Here we have scale, so we can have all possible resolutions. So in other words, actually, like some foods, they are better handled with a fork than a spoon. For example, if you want to have noodles, then we go for fork. If you want to have smooth food, then you go for a smooth spoon. So the selection of the spoon depends on the type of food, and wavelet gives you such a kind of basis functions which can be suitable for analysis of any signal. If your signal is it requires low resolution time domain, you have such a scale there. You want to have good frequency resolution, you have that suitable scale there. So all possible scales are there, and you have to select a scale, and what we do analysis of signal with all possible scales, and we assume that at least one scale will match our requirement. So that is actually, so now it is the generalized version of STFT, and where you have all possible scales, all possible windows, all possible durations of the window, all possible bandwidths of the window, all possible spread, all possible resolutions of the windows. So that actually that the use of scale, and scale is a very, very important parameter. In signal processing that we have seen in the short STFT time frequency, there are three independent parameters. One is time, second one is frequency, and third one is scale. So whatever is happening in this world, it has connection with time, and whatever we listen, it has connection with frequency, and whatever we see, it has connection with scale. So now signal processing, the use of scale is now a lot of actually taking place. People are developing algorithms based on the scale concept. So old time it was time and frequency, now it is time and scale, and like lot of interest in the literature to explore concept of scale. And scale makes sense. So when, like for example, when you see something, scale is meaningful. So like a wavelet is very popular in image processing. So for example, suppose you want to see the elephant, and if you see the legs of the elephant looks like a tree. If you see the tail of the elephant looks like a snake. But elephant is not a tree, elephant is not a snake. If you want to see elephant like elephant, then you have to see at proper scale. So when you see at proper scale, and you have nice meaningful information. So these biomedical signals, many other signals we don't see at proper scale. So this whatever information we extract, it may not complete information. So by using this scale concept, we can see the actually proper signal at proper scale, and by doing that, we can have meaningful analysis. So that is the one of the actually major advantage of scale. So now we will see how to use scale for this wavelet transform. So here actually this wavelet, it works well when you have low frequency component and high frequency components both in the signal. So for low frequency component, you want to have a wide window for analysis, and high frequency component, they exist for a small interval, so you want to have a narrow analysis window at time domain. So that actually can be obtained by using different scales. If your signal has nearly frequency component, they are same, then I think STFT is better choice as compared to wavelet. So wavelet makes sense only when your signal has continuous nature of the data, discontinuous nature of the data. So where you can use different scales for the different parts of the signal. So when you have low scale, then it gives you good time resolution, poor frequency resolution. When you have large scale, it gives you a poor time resolution and good frequency resolution. So this is the mathematical expression for continuous wavelet transform, and it's actually the signal that we want to analyze. And psi t is not a mother wavelet, and by using this tau and s, tau is the shifting parameter like STFT, and s is the scaling parameter. So here we use these two parameters, shifting and scale, and by doing that we generate daughter wavelets from this mother wavelet, and we use 1 by √s. This is normalization constant, and it ensures that the whatever daughter windows, these wavelets we design, they have similar energy or similar properties like the mother wavelet. So even each daughter wavelet also can be used as a mother wavelet. So it is like a big library. It is a lot of options are there that are very useful for signal analysis. And here also you can see this in frequency in the output of this transformation the two-dimensional. So like this CWT continuous wavelet transform is a function of time and scale. So here earlier it was function of time and frequency. So STFT, short time Fourier transform based time frequency analysis, is also known as time frequency representation. And here this is actually, it gives you output in time and scale. So due to that, it is also known as time scale analysis or time scale representation. And this frequency is inversely proportional to scale. So time is frequency representation also can be obtained using this time scale representation. This is very interesting example. Here you can see the same example we have taken like STFT. And here in the beginning we have a high frequency component, then low frequency component, then high frequency component. And here we have selected this wavelet or window corresponding to scale 0.1. This is low scale. So it has good time resolution and it is very suitable for the high frequency component presented signal. Again, we will choose another window that is of large scale. So it is now 0.5. So it is suitable for the middle part of the signal. Again, we are changing the scale. So we are increasing scale. So it may be suitable for other part of the signal. Then again, we have increased the scale. So maybe like this second case, this scale is suitable. So what we are doing, we are analyzing signal with all possible scales. And we believe that at least one scale will match with the requirement, with our required resolution. So this is actually history that is for this whatever signal processing techniques for time frequency analysis. Shannon around 1950, he come up with the sampling theorem. And he says that signal can be represented in terms of samples, in terms of impulses. And each impulse is well localized in time. So that also can be represented as a time frequency representation, where time we have very good time resolution and very poor frequency resolution. In case of Fourier actually in 1807, he represented signal in terms of impulses in frequency domain. That what Shannon did in time domain, that Fourier did in 1807 in frequency domain. So that actually Fourier method gives you very good resolution in frequency domain and very poor or nearly zero resolution in time domain. And that is why without actually knowing sampling in time domain, Fourier sampled signal in frequency domain. So due to that, actually many books, French books especially, they consider Fourier as a Newton of France. Actually Newton, because without knowing sampling in time domain, he sampled a signal in frequency domain. Geber represented signal in time frequency domain with the help of fixed resolutions in terms of window functions, which has fixed resolution, fixed time and frequency resolution. And wavelet gives you multi-resolution analysis that you can see at any point of time you have multi-resolution properties. So for example, in the first tile you can see your low scale, it has good time resolution. When you go for large scale, it has poor time resolution. So that at a given point of time you have good resolution, good time resolution also, poor time resolution also. So all possible resolutions are available at any point of time. And whatever resolution is required, that will be obtained by some particular basis function. That is the actually concept of wavelet. And it's a history. In 1970s, Morlet, he was a geophysical engineer. He came up with the idea of this wavelet, and people were having problem with the STFT, short time Fourier transform. They say this wave fixed. It has fixed resolution. Once window is fixed, then we cannot change it. So then this Morlet, and he come up with the idea of wavelet. He says you used to use scale concept in the wavelet, and actually he used to work in the field. So he was aware with the concept of the scale. So then in 1980, Grossman, he was the first person who formalized this transform formally and come up with the first wavelet transform mathematically in formal way. He presented to literature. In 1984 to 85, Meyer developed orthogonal wavelet basis functions with better time and frequency localization. And Duvechi, she has done a lot of work in wavelet and this is one of the pioneer, and you can find like DB1, DB2, DB3, DB4. Based on her name, various wavelets are there. Which is 1, which is 2. And Stephen Mallat, he proposed this multi-resolution analysis. Actually, his PhD thesis was on this Mallat algorithm that we use for image compression, signal compression these days. He also proposed discrete wavelet transform and cascade algorithm for computing discrete wavelet transform. Vitaly and Zelena, they from Ecole Polytechnic, this group actually they have done a lot of work on wavelet and filter bank. They have also extended these filters for multi-dimensional signals like image and videos. So this scaleogram, actually like in short-time Fourier transform, square of the magnitude of STFT, that is known as spectrogram, and here this square magnitude of the this time scale analysis or continuous wavelet transform, this is known as scaleogram. So this scaleogram is also a nonlinear operator, and it can contain cross terms when frequencies are very close to each other. So how to compute a scaleogram in MATLAB? There is a CWT command in MATLAB. It requires selection of scales, so that actually can come through some experience. And as the signal that you want to analyze, and wavelet name is required. There are various wavelets, hard, wedges, and you can select according to your requirement. Then plot, it gives you spectrogram and scaleogram in MATLAB. So this is one example. You guys can see this is the signal in time domain, and this is the obtained scaleogram. So here you can see the signal has actually this is finite signal in triangular shape, and so it has infinite frequency components. But when you go for time scale representation, you can see it has infinite frequency components, but different resolutions. So at low scale, you can have good time resolution. At large scale, you have poor time resolution. But all frequency components are present. But when you compute same thing with the short-time Fourier transform, you will have fixed resolution. But here you can see that like this triangle is becoming inverted cone kind of thing. So that is area is changing at different scale. You have different span of the signal. So that is the different resolutions. At low scale, good time resolution; large scale, poor time resolution. So in this is actually MATLAB code. You can use I will share these slides with all of you, and you can try this use of CWT command to obtain such plot. And this is another example where this frequency is decreasing with respect to time. So like in the beginning it is 30 Hertz, then 20 Hertz, 10 Hertz, 5 Hertz. And when you apply this time scale analysis using this CWT continuous wavelet transform, then you can see nicely that this scale is changing, scale is increasing with time, because this frequency scale is proportional to 1 upon frequency. So this time scale representation shows this frequency is increasing with respect to time. So when you compute time frequency representation from this time scale, then it will have frequency will be decreasing with time. So that whatever signature we have in signal, that can be obtained from time scale representation. So now how to compute this continuous wavelet transform in MATLAB in computer or using machines. So then actually we need to discretize the parameters, that is shifting and scaling parameter needs to be discretized. So when you discretize these parameters, scale parameter and shifting parameter, that gives you discrete wavelet transform, DWT. And this is the this Mallat actually concept. He represented this discrete wavelet transform based on the filter bank concept. So like you have signal xn, this is the discrete time signal that we want to analyze. Then this signal will go through high pass and low pass filter, and then it will be downsampled by 2. So this what we believe, this high frequency components which are present in the signal, that we cannot listen and we cannot perceive from our eyes. So better to throw them. So what we do in this algorithm, we don't consider high frequency components. We always perform decomposition of low frequency components. So this high frequency component is known as detail, and this low frequency component is known as approximation. So this first stage, this is the detail approximation. Then again we will perform decomposition for approximation. So again we have detail and approximation, and that way. So this is first, this is second stage, 2-level decomposition, and that is actually reconstruction process. So this first one, this is known as analysis, and second one is known as synthesis process. So here actually we don't touch detail, we always perform an analysis of approximation part. So that is approximation is like a low frequency part and detail is the high frequency part. And then this reconstruction of the signal can be done. So whatever is your interest in particular band, particular coefficient, you can modify them, you can throw them, you can keep them, and after doing the suitable operation, you can convert signal again in time domain. So the same discrete wavelet transform algorithm also can be shown in terms of the samples. Like every level, the sample length becomes half. So you have 512 samples, then it will go to 256 samples. It will divide due to downsampling operations. So in the end, like if you are performing this up to third level decomposition, so then third level you will have approximation, and detail at third level, detail at second level, detail at first level, like that. So sometimes we can also use this DWT discrete wavelet transform as a spectrum representation like Fourier. So if you plot A3, D3, D2, D1, then it looks like a one-to-one mapping between time domain and frequency domain. So it can be also used as a spectrum of the signal based on the DWT. So how to compute this discrete wavelet transform MATLAB? There is DWT command, and which requires signal and wavelet name, and that gives you approximation detail. So here you can see this approximation detail, and after that, if you want to decompose again CA in terms of approximate detail, then initial signal you can give again CA as input, then it will decompose, DWT will decompose this approximation in terms of approximate detail for another step. So in that way, we can use this algorithm in iterative manner. So like whatever approximation you have received with the previous level, it will become input for the next level. And next level, whatever you get input, it will be input for the next level. So in that way it works. So there are various wavelets like Duvet's. You can see this is the low scale, and Haar. So Haar, this is the lower part shows the plot low scale, and the upper part shows the high scale. You can see that. So when you have signal as continuous nature, then we go for Duvet's kind of wavelets, and if your signal is discontinuous in nature, then we go for Haar, because Haar is suitable for discrete nature of the data. That you can see, even mother wavelet also looks like a discontinuous, and Duvet's it looks like continuous. So based on the nature of the data, we can also select the wavelet. So there are various applications of the wavelets. First one is actually that this is a simple example which will show what is the use of this decomposition, like what it does. So you can see the signal, first signal, this signal has noise, and so signal is low frequency part and noise is high frequency part. So when you apply this first level decomposition, it gives you approximation and detail. So approximation, you can see there is less effect of the noise, and the detail, this is noise only. So again we will apply this discrete wavelet transform for this approximation signal. Again it will remove noise, and that way it will continue till noise is removed from the signal. And then from the last, from this coefficient, we reconstruct signal back. And whatever the subbands we have corresponding to noise, that we will not consider in the reconstruction. We will remove them. We will make them 0 instead of this coefficient values. So this coefficient value will be 0 in the reconstruction. So indirectly, noise is removed from the transform domain, and we can reconstruct the signal in time domain, and that is enhanced signal. So that how to implement this discrete wavelet transform in MATLAB, there is wave menu command. So if you search on this command window, just put wave menu type, and automatically this window will appear, and it has all options, whatever window, whatever wavelet you want to use, mother wavelet, what is the level, up to which level you want to decompose data. This are all flexibility. So you can load your own signal, you can take from the MATLAB library. So here you can see the signal, whatever is taken, it is decomposed up to 5th level. So 5th level means it will give you 5th level approximation, and all for detail at 5th level, detail at 4th level, detail and 3rd level, detail 2nd level, detail and 1st level. So in that way now, according you can see whatever you based on these bands, you can perform analysis, and even you can extract features. You can perform classification of the data. So these features are very unique representation of the data, and a lot of things can be done. It has many applications. Some of the applications include compression, denoising, feature extraction, discontinuity detection, data analysis, which include biological data, that is good for health, and many people earn money also using Wavelet, that is financial data. So like you can study this financial data in order to understand the market, what is going based on the financial data. So this is one example. You can see this is the signal, and these are the obtained coefficients, Wavelet coefficients. You can see the signal has many significant values, but these coefficients are having very less significant value. This signal is represented with the help of fewer coefficients. So here nicely, these coefficients are nearly zero. So that actually leads to the compression. So that we can draw them. So this that gives you the saving of the memory. You can store data with the help of very less number of coefficients, and which results, so like you can store more data in transform domain as compared to actual data using this Wavelet based method. So here you can see this is a various like a percent, like this perfect reconstructed signal, and this is the 75% compression, 81% compression, 87.5% compression, and here you can see this is 93.7% compression when we are taking only one coefficient out of 16 coefficients. So that is actually still you can see the whatever signal we have reconstructed from these fewer coefficients, and that is actually preserving the structure of the signal. So that is even after compression also your signal is looking similar to the actual signal. This is another signal, that is electrocardiogram signal, ECG, which measures electrical activity of the heart, and you can see this is the original ECG signal, and these are the ECG signals obtained after performing compression. So like this 50%, 75%, 87.5%, 93.5%, and in this case you can see this PQRS pattern, which is useful for diagnosis, is still preserved in the signal after compression. So that it is very useful concept for telemedicine. Like in rural areas we don't have sufficient doctors. So this telemedicine concept can be used, where instead of sending ECG signal, we can send these coefficients, and at the receiver side, the hospital doctors, they can perform this inverse discrete Wavelet transform, and they can reconstruct the signal. So in that way, like here, this compression 16 times more data can be transmitted. So that is actually very efficient telemedicine can be done. So that is useful for health monitoring. So like many countries, for elderly people, we want to monitor the health using biosignals. So these signals can be actually transmitted, which will require less memory. So due to that, processing will be faster, and due to this less number of data, less amount of data, this algorithm will be suitable for real-time implementation. This is another example, denoising. Here you can see this is the signal that has noise, and this is the decomposed signal up to 5th level. So here you can see this D1, D2, D3. These are the details at the first level, second level, third level. They look like noise. And other components, approximately 5th level, till at 5th level, 4th level, they look like signal. So that actually we can group them. So signal part can be degrouped, and the noise part can be removed, so that enhanced denoising can be performed, and you can obtain the enhanced version of the signal. This is another example where we can detect discontinuity using discrete Wavelet transform. So here this is the signal, and signal has discontinuity, but it is not visible from the data, from the signal. So you perform this first level decomposition, you will have approximation at first level, detail at first level, and detail at first level has discontinuity, you can see. So that actually, so it gives you the discrete Wavelet transform also helps us to decompose data into two parts. One is continuous part and discontinuous part. So this is very good for actually power quality assessment, like power quality, sex, well, there are various distortions, and such a multi-resolution approach can detect these distortions in power quality assessment. Same, this discontinuity detection also can be performed using this continuous wavelet transform CWT, and that is scaleogram. So when you scaleogram, this discontinuity will have, because it has all frequency components, so it will be associated with all scales present in the signal. There is another time frequency technique, that is actually Wigner-Ville distribution. It is different kind of, it doesn't use basis functions like Fourier and Wavelet. And this Wigner actually received Nobel Prize in Physics 1963 for this contribution, and he was from physics background, and Ville was from field of communication. So actually they work together and they come up with due to this joint efforts, this is also known as Wigner-Ville distribution. So that is actually they explored this. It was invented in physics, but they explored in signal processing, and this is actually in nature it is quadratic time frequency representation. So due to this quadratic nature, it contains cross terms. This is the major limitation of the Wigner-Ville distribution. But theoretically, it has infinite resolution in time domain and frequency domain. So in time domain, it is defined by this mathematical expression, and you can see here we are integrating entire time. So due to that, it has excellent resolution in frequency domain. And when defining frequency domain using Parseval concept, where you can see this is have excellent resolution in time domain. So that is actually absence of window gives here. This is one of the classical time frequency technique. And for monocomponent signals, if your signal has only one frequency component, especially linear chip kind of signals, it is perfect time frequency representation because it gives you infinite time and frequency resolution. But when you deal with the multi-component signal, then it includes cross terms in the analysis, and which is very misleading. So that we will see with the help of some examples. So this is the signal, multi-component signal, which is the superposition of monocomponent signals. For example, this signal has m monocomponent signals, and when you apply Wigner-Ville distribution, this signal it will have auto components and cross components also. So these cross components will create the problem in the time frequency representation, and sometimes they give misleading interpretation of the analysis. So this is one of the example. In signal, we have this signal is a mixture of two chip signals. One is this is positive chip signal, it is increasing frequency, and other one is negative chip signal, that is frequency is decreasing with time. So when you apply this Wigner-Ville distribution to this mixture of these two components, then it gives you cross terms that you can see that time frequency representation. These cross terms are coming due to this definition of the Wigner-Ville distribution. For two components, so instead of two components, now time frequency domain shows three components. So that third component is misleading. Similarly, this is another example. Here you can see it is a mixture of two signals, and one signal, both are positive chirp signals. So, but in time frequency domain, it shows three chirp signals, three frequency component. They are changing linearly with time. So this is misleading. And in fact, it has only two components, but the third component is coming due to this Wigner-Ville distribution, due to multi-component nature of the data. And third signal, this is actually it is mixture of two time-limited and band-limited signals. So you see this, this signal in time frequency domain, it has three time-limited and band-limited signals. So here this middle term is coming due to cross terms. So there are various methods in signal processing to reduce these cross terms. One kernel design, wavelet decomposition, perfect reconstruction filter bank, Fourier-based decomposition that is actually proposed by us, and image processing based methods. So people use various signal processing techniques to reduce these cross terms, and this Fourier-based decomposition based approach provide this cross terms free time frequency representation. You can see now this time frequency representation, they are free from cross terms. So there are various time frequency representation actually based on Wigner-Ville distribution. So this link will give you various codes which are available for implementation of such kind of time frequency representation. which are based on Wigner-Ville distribution. And recently, another time frequency technique has come. It was actually proposed 1998. That is known as Hilbert-Huang Transform, HHT. And that is actually, it doesn't use any mathematical form of the signal. It doesn't use basis functions. It doesn't have analytical formula. It is an algorithm. It has come from computer science. So actually, this algorithm performs decomposition of the signal in terms of like in Fourier, we represent complicated signal in terms of simple signals. Here also we represent complicated signal in terms of simple signal with the help of algorithm. So this Hilbert-Huang transform includes two parts. One is empirical mode decomposition. Second one is Hilbert spectral analysis. So empirical mode decomposition, it provides a set of simple signals, and like in Fourier it was sinusoidal functions. But in case of empirical mode decomposition, we allow the parameters of the sinusoidal functions vary with time. So like it can be amplitude sinusoid, amplitude modulated sinusoid, frequency modulated sinusoid, or amplitude and frequency modulated sinusoids. So these such kind of simple functions are known as intrinsic mode functions. Intrinsic because these functions they are extracted from the signal. They are actually like in Fourier wavelet, you are designing basis functions from our side, and they are independent from the signal. But here, these basis functions, whatever you obtain, intrinsic mode function, they are part of the signal. So by using algorithm, we extract these components from the signal, and that due to that this is known intrinsic mode function. So they are like post basis functions. They are like in Fourier wavelet, these are the pre-basis functions. So from when we perform analysis of the signal, we design a priori these basis functions. In case of EMD, we don't design a priori basis function. By the algorithm, we extract from the signal. So that is actually we use algorithm. So this is algorithmic decomposition. And after obtaining these simple components, intrinsic mode functions, IMFs, we apply Hilbert spectral analysis to obtain amplitude envelope and disturbance frequency of these IMFs. And this amplitude envelope and disturbance frequency of these IMFs provide time frequency representation. So this EMD method actually is data dependent, doesn't require any condition about the stationarity. It is doesn't require any condition about the whether system is linear, non-linear. It just give data, it will decompose. So it needs just only data. It doesn't assume any structure of the data. It doesn't require any conditions of the data. And it's IMFs, whatever we obtain intrinsic mode functions, they should satisfy two conditions. And this complete data set number of extrema and number of zero crossings must be the same or differ at most by 1. So this condition ensures that these IMFs, they are like sine cosine functions. And the mean value of the envelope defined by the local maxima and local minima is 0. So this condition ensures that whatever is IMFs are obtained, they are symmetric in nature. So the symmetric sine cosine functions nature with the property of the varying amplitude and frequency functions is very useful for signal analysis that we'll see. So this is simple algorithm for computing EMD. We determine a signal, we take signal, then we determine upper and lower envelope of the signal, and then this is done by the maximas and minima. So we obtain minimas and maximas from the signal, and we interpolate them, then we get the upper envelope, lower envelope, and then we obtain the average of these envelopes. So that actually gives you mean value, and this is indirectly stages mean of the signal. So that it should be 0 in order to this IMF should have symmetric nature. So due to that, actually we subtract this time varying mean from the signal, and this whatever residual we obtain, we check this whatever these two conditions I have mentioned. If this residual is satisfying these two conditions, then it is IMF. Otherwise, we have to repeat again. Initial signal we take residual and we repeat this entire process, and we continue till we get IMF. So once our IMF is derived, then we subtract this IMF from the signal, and then residual entire operation will be performed on the residual again. So in that way, one by one, we extract all possible IMFs. So this is one of the example that is actually very simple example. It shows how EMD works. So this is the signal that we want to decompose using EMD method. So determine the maxima, then interpolate them, determine the minima, interpolate them, and then we obtain the mean of these two envelopes. So now we subtract this mean from the signal, and then this is the residual. So this residual doesn't satisfy these two conditions of IMF. Then again we will, instead of signal, we will take this residual, and then again we will perform same operation, determine the maxima, obtain envelope, determine minima, obtain envelope, then determine the mean value of these two envelopes. Then again this residual doesn't satisfy these two conditions of IMF. So in that way we will continue till this mean becomes 0. So you can see here this instantaneous mean, this is the average of this upper envelope, lower envelope, that is nearly 0. So in that case, this residual now it can be considered as an IMF. So we will take this outside and we will subtract this IMF from the signal. Then whatever residual will come, then we will take as input. Again, we will do same process. We will take other IMF. So in that way, we obtain IMFs. And this is actually this is an electroencephalogram signal, that is it measures the electrical activity of the brain, and this is also known as EEG, termed as EEG signal. And we perform this EMD decomposition of this healthy EEG signal, and that is the first one. This is signal, and these are the obtained intrinsic mode function IMF. So this first IMF is corresponding to low scale. This is like detail of the data. And last IMF with the large scale component, that is the approximation of the data. So this is actually this all components, whatever we obtain this EMD process, they are arranged from high frequency to low frequency, or low scale to high scale. So or detail to approximation order. So that is recent research has shown it is also whatever EMD performs, indirectly is performing wavelet decomposition. And here you don't need to choose any wavelet function, no mother wavelet, no which level you want to decompose, nothing is required. This is adaptive process. You just give signal, it will give you the components. And Hilbert spectral analysis uses Hilbert transform. So this is a signal, and then we take Hilbert transform the signal, then we make complex signal by using signal plus J times Hilbert transform, and it gives you analytic signal. And from the analytic signal, we can determine the amplitude envelope by taking magnitude of the analytic signal, and derivative of the phase of this analytic signal gives you instantaneous frequency. So this is one example. You can see the signal and this spectrum, and the signal has time varying frequency components, but it is not clear from the spectrum. So what we do, we decompose signal into IMFs. So this first IMF, second, third, and so this is high frequency to low frequency, or detail to approximation. And then we apply Hilbert transform. Now you can see it gives you complete picture of the signal, time frequency representation. And here 700 hertz, 700 hertz is 2 times it is this frequency repeating. 600 hertz is repeating 2 times. But from spectrum, it is not clear what time this frequency is occurring. Various machine learning algorithms, they are taking this as an input, and you can come up with the classification of various normal and abnormal data. Detection, analysis, classification. So it is very good. It is in form of matrix, time frequency. This plot, this also can be converted into form of matrix. It also can be converted image because the time frequency magnitude is always positive. So this also can be considered the intensity of an image. So that when you have this image kind of nature, a lot of interesting signal processing can be applied on time frequency image. So it gives you a lot of scope for future work. It can be connected with many areas of science and technology. And this is the conclusion. Time frequency representation is a general representation of frequency domain representation, similar to non-static signal, which can be considered as general representation of a static signal. And there are various problems in time frequency, like short time Fourier transform, selection of type and size of the window function. There is no rule which will suggest us which window should be used and what should the size of the window. Wavelet transform, there are no rule how to select the mother wavelet, how many levels decomposition should be performed. Wigner-Ville distribution, there is presence of cross terms. Hilbert-Huang transform, there is no mathematical theory, though mathematical formula. And so there is time frequency representation is an active area of research. And these are some references. You please go through them for more details. And Thank you very much for your time, for time frequency analysis.